Alright, so this is a demo of a comparator that will have an LED on when when a binary input is less than 8 or greater than 12. So here we have our truth table. This is essentially just counting in binary from 0 to 15. And we have this group. This group of zeros is below 8, and this group of zeros is above 12. And we need the zeros to be able to turn on our LED without hurting the circuit. So the way that we can achieve this is we take our A3 input, because A3 is below 8, because this is a 7 here. We invert it, so we get a 0 if A3 is on. Then if A3 is on, we take the 0 from there, and it will go here, and then we invert it into a 1. But if A is greater than B, which B will be set to 12, then it will put a 1, put it here, so this will be a 1, and we'll have a 0. Another way to do this, using just one type of gate, is to have an NOR gate. So we use the NOR as essentially an inverter. We put A3 and wire it up to both of the NOR sides. That inverts the signal, and then we put it down into an NOR gate with A is greater than B. So this is kind of what the circuit looks like. For all of these inputs here, there is another path to ground that goes through resistors. That's just really hard to draw without making it look super messy. So here's my circuit. Right now the B group, as you can see here, which is these 4, 1 through 4, is set to 12. This would be B3 and this would be B2, so 8 and 4. So let's try out our truth table. So it's already set to all zeros, so that looks good. The light is still on. Now if we turn on A1, that is 1, the light's still on. If we do, or sorry, that was A0, this is A1. If we do A1, that's 2, and the light's still on. So now if we do A1 and A2, that's 3. Now if we give it an input of 4, so I turned on 8 there for a second, the light is still on. 5, the light still remains on. 6, 7, but when we turn on 8, the light will turn off. I have 12, so hold on. Okay, when we have 8, the light will turn off. And it will remain off for 9, for 10, for 11, and for 12. But as soon as we get above 12, so that when we're at 13, it'll turn back on. And at 14, it'll be on, and at 15, it'll be on. So this matches what we needed from our truth table. And that's my circuit demo.